Thank you very much. I'm very happy to be here. Let's make this talk completely informal. If you have any question during the talk, just come, ask, raise your finger, and I would be very happy to answer. Don't wait until the end. So, as said, I'm from Tel Aviv University. I head the deep learning lab at Tel Aviv University. At the deep learning lab, we have multiple projects in all domains, all application domains of deep learning, including image analysis, text analysis, robotics a little bit, and voice analysis. And what I'm going to describe today is the marriage of image analysis and text analysis. And I'm going to describe 3 different tasks. So the first task is the task of image annotation. In image annotation, we have an image, and we have a data set of possible sentences that describe this image. And we would like to automatically find the sentence which describes the image. The second task, task number 2, is the one of image search. We have a sentence, and we have a data set of images, and we need to find the matching image out of this data set. The third task that I'm going to describe, this is maybe the holy grail of computer vision, is the task of captioning. Given an image, we never saw this image before, the system needs to output a new sentence in English.
2 girls playing soccer.
And I'm pretty amazed that through the power of deep learning, we are already able to tackle such tasks. So I'll describe the technical agenda. We are going to describe our image representation. This is going to be very short because we just use the workhorse of deep learning in computer vision, which is convolutional neural networks. And then I'm going to describe how we represent the sentence. Then I'm going to move on to how to combine images and the sentences together. And then I will present very shortly how to create new sentences. So for image representation, we use a network that was trained in Oxford, a convolutional neural networks that was trained on ImageNet, starting from an image, going through many convolutional layers, coming out with 1,000 different classes. We just take the representation from this layer over here, and this is a vector representation. It's just a vector of activations which we use to represent the image. So the input is an image, goes through the network, and we pull the vector from this location. With regards to sentence representation, so we are not natural language processing guys, we are computer vision people. We thought, what is the most natural way for us to represent sentences? So we figured, well, let's use local descriptors and then use pooling, just like we do in computer vision. So what would we use for local descriptors? We use Google's word2vec. I will mention it in a second. And how to combine, pull the local representations into one vector representation. This is what the major novelty of the work is about. I will describe it. It's a new type of Fisher vectors. So what is word2vec? Word2vec is a system by Mikolov and colleagues which maps words to vectors. So every word is mapped to a vector in R300. So every word mapped to a different vector. And these vectors capture very well the semantic meaning of the words. So if we have the word Python, and we are looking for the words which are most similar semantically, then we get a list of words, scripting, bash, Perl, and so on. And this is out of a dictionary of all English words, not just programming language words. So we start with a sentence. A man is playing guitar. And every word in this sentence we describe by a vector. So the word a, playing, guitar, every word represented by a vector. Then we need to take all these vectors and pull them together to one single vector. The reason that we would like to pull them together is that machine learning algorithms prefer to work with vectors and not with sets of vectors. So we pull all these vectors together to a single vector. This is being done in our system using something which we called hybrid Gaussian-Laplacian mixture model Fisher vector, which I'm going to describe next. This is a generic way to create a text representation. In any NLP task that we would like to approach, we can take the text, we can apply this hybrid Gaussian-Laplacian mixture model Fisher vector, and get a representation. So what is this hybrid Gaussian-Laplacian model? In essence, if we consider the Gaussian distribution and the Laplacian distribution, we started our work by noting that Gaussian distributions, and I will get back to it later on, are not very appropriate for describing text. So we thought, well, let's use the Laplacian distribution, but it only got us that far. It's not much better than the Gaussian distribution. Then we decided to combine the Gaussian distribution and the Laplacian distribution to a hybrid distribution. We take the Laplacian distribution to the power of b times the Gaussian distribution to the power of 1 minus b. This is in 1D. Now we want to create multivariate distribution. We just multiply independent dimensions. And this is just one component. We actually use a mixture model of multiple components. We just sum k different components. In order to estimate this from the data, we have an EM algorithm. The estimation step is fairly straightforward. The maximization step needs to estimate both the parameters of the Gaussian and the Laplacian, and this mixing coefficient b. It turns out that this b is going to be either 0 or 1. The two values that we are going to get are 0 or 1, no values in between, which is actually very convenient. It cuts the number of parameters that we need to estimate by half. Then we derive the Fisher vector out of this mixture model. The Fisher vector is the derivation of the likelihood by the parameters of the model. So we have for b equals 0, we derive according to the Gaussian parameters. For b equals 1, we derive according to the Laplacian parameters, and we get the Fisher vector. The Fisher vector is the first step in representing the set of vectors as a single vector. We actually need to normalize it. To normalize, we need to compute something which is called the Fisher information matrix, which involves a lot of algebra and approximations. So let's go back to the application itself. We had images and we had sentences. So images, we take convolutional neural network, we extract the representation, and we get a vector. For sentences, we take the text, we extract word to vec, we apply EM to get the hybrid distribution, we get a Fisher vector, and at the end of the day, we also get a vector that represents the sentence. Now we need to combine both together, bring them to a common space. We use a classical algorithm, canonical correlation analysis, for this task. Later on, I will discuss extensions. What the CCA algorithm does, it computes a projection matrix from the space of images and from the space of sentences to a shared vector space. So now that we have a shared vector space, we can combine the images and the text together. So to perform image annotation, what we need to do is to take the image, take the sentences, project all the sentences to the shared space, project the image to the shared space, and just look for the sentence which is closest in this shared space to the image. If you want to perform image search, it's basically the same. we project the sentence, we project the images all to the same space, and we get our solution. So the only task that I haven't showed so far is how to perform sentence synthesis. So one would think that you need a very elaborate English model in order to do it. Maybe you need also object detection model and combine different detections. The way that this is done today is using recurrent neural networks that take images and match in sentences and are trained to produce such sentences. So I will describe our system for this, and there are other concurrent systems that also do image captioning. In our case, it's slightly easier because the images and the sentences are in a shared space. So we can have a uniform recurrent neural network dealing with both of them equally. So we start with the input image. We project it. We actually compute a representation using the convolutional neural network. We project it using the CCA algorithm, and then we provide it to the recurrent neural network. Here it's a specific type. It's an LSTM network. And from this network, there's an output, which is the first word of the sentence. In this case, the word to. We take the word to, we compute the word to vector representation, we compute the hybrid Gaussian Laplacian mixture model Fisher vector, CCA projection, and now it's in the same space as the image. We feed it to the LSTM, and we get the second word, the word girls. Yes, please.
How do you distinguish between girls and boys, for example? In this case, I can probably do it using my natural intelligence.
So I think there's a, I can bring up a larger image. It's actually quite distinguishable that these are girls. And I will show some examples in the next slides. And you can also ask similar questions. How would it know that it's a ball and not a tomato, and so on? There are priors created by the dataset, and there's some visually sparkling information that helps you. In this case, it's rather easy to see that it's girls. But let's see the other examples, and I will discuss the limitations of the system. Maybe it will become clear. OK, we feed the word girls to the network the same way. We continue this way until we get the end sentence. So basically, from the image, in an automatic way, we were able to create a full sentence that describes the image. So there are several other systems, captioning systems made concurrently. Our system, which you're able to access yourself and test it for yourself, it's available at imageannotator.cs/ACIL, is actually kind of nice in that it's very liberal. It produces new sentences, not just sentences that it saw during training. So I will show some examples. I will start with the good samples, and then I will move on to more and more embarrassing examples. So this is a dog with ball in its mouth. This is a basketball player in the uniform is running in the air. Here are a few more outdoor images. A man in red shirt is climbing up the rock face. A boy is jumping into pool. So here you can start to see the major limitation of the system. Basically, it decides what to describe, ignores, for example, the dollar bill, and it doesn't provide yet a complete description of the image. It just comes up with a reasonable description of an image when it actually works. So in another image, two dogs are playing in the water, and it's actually OK, because the system was only trained on 8,000 different images, and it never saw a bear before. So the closest it could get is a dog. So two dogs are playing in the water. But of course, there are much more embarrassing mistakes. For example, product images, it doesn't do very well. There were no training product images. And sometimes it just hallucinates all kinds of weird stuff. and it can even mix a dog or a cat and so on. So this is with regards to image captioning. Let's move to image annotation and image search. And there it's much easier to directly compare to other systems. And as you can see here, our system is in blue, and this is accuracy numbers. We are much better than all other concurrent systems by all major labs. This field of image captioning and image search annotation became very popular in the last year. For image annotation, we are on all major benchmarks above the other concurrent systems. For image search as well, we are leading with regards to performance on all 4 acceptable benchmarks, and we are still improving. So I described images and text. Any other questions by this point? Yes, please?
So it looks like the reason you are winning, the thing that gives you the edge is the Gaussian Laplacian which. Can you describe the vision behind it? It's kind of really weird that you, for some problems, you get one solution for another.
That's a great question. Indeed, there is a huge difference if we just use Fisher vectors out of Gaussian mixture models, which is the usual Fisher vector used in computer vision, and the model we propose. In 2 or 3 slides, I will give something that will provide a little bit of intuition, so let me just defer the answer until we get there. Any other question?
Yes, I have a question here.
Yes, please.
Image captioning result of synthesis, the way you call it. So have you compared your methods in this Microsoft Coco competition that was run in India?
So for captioning, we did not compare. We just didn't have the resources to apply RNNs on the scale that we need in order to be competitive for captioning. But for annotation and search, we are able to compare with any system very favorably. However, for captioning, if we want to be really competitive with those systems, we need a lot more resources, a lot more GPUs, train on many more images. And 8,000 images for our resources were about the limit that was reasonable. Already took about 2 weeks to train.
What kind of hardware?
So we just use NVIDIA Titan GPUs. So the system, as you see here, is trained on just 1 GPU. Yeah. Other questions? Yes? So the final dimension of the common space is 4,000. Other questions? Yes, please?
Is there any prospect of expanding this method to other languages rather than English?
So currently we just did English. In another work that we did, we actually used a similar kind of method in order to map between 2 different languages, Hebrew and Arabic using newspapers, and Hebrew and English using Bible translations and such. In this work, it's only so far just for English. Any other question? Good. Okay, so I will move to a few NLP topics. As I said before, the new representation is very generic. It can be used to any type of NLP task. So although we are not NLP people, we figured let's try other NLP tasks. And in this work, we extended the model a little bit. So if we before talked about this is the Gaussian distribution and the Laplacian distribution, this is the hybrid distribution that combines both. We figured let's take it a step further and use generalized Gaussian distribution, which is a distribution that if you put here p equal 2, you get the Gaussian distribution, p equal 1, you get the Laplacian distribution. We figured let's use this. It's a little bit more general. And the intuition, to answer Arkadi's question from before, is that if you look at word embeddings, such as the word to vec representation, and these are the 300 dimensions of word to vec. And here is the coefficient that you get from the generalized Gaussian distribution when you fit each dimension, you can see that most of the dimensions are not really Gaussian. If you apply PCA, you try to improve, make it a little bit more Gaussian, then still it's slightly below 2. It doesn't sit at 2. Many times it's actually better to use ICA. So in word-to-vec representation, you want to improve it, just apply ICA. And here it's of course even worse. It's not Gaussian at all. And this is actually an artifact of ICA. ICA pushes away from Gaussian distributions. And you can see that you get coefficients starting from below 1 all the way to 2, but most of them are not Gaussian distributions. So what we do in this work, we generalized what we discussed before to the case of generalized Gaussian distributions, and we apply Fisher vectors on top of mixture models, and I will now describe the applications. So one application is the one of answer-centered selection, and this is, again, a competitive application started with IBM Watson. You get a factual question, what is the brightest star visible from Earth? And you get a list of candidate sentences. So some search engine pulled up sentences, and you want to find the sentences which contain the answer. So in this case, there are 2 sentences that say, Sirius, the brightest star in the heavens, or the brightest star visible from Earth, contain the answer, and we would like to find out these sentences. And applying this benchmark using our methods, here again in blue, we get a sizable improvement over previous work, including other deep learning work by Google. And now we'll move to another task. This task is the semantic sentence similarity. We are given 2 sentences, and we would like to know whether the 2 sentences are related or not. So if we have a woman is riding a horse and a woman is riding a donkey, maybe somewhat similar. If we have someone is drawing and someone is dancing, then it's almost entirely unsimilar. We have a score between 0 and 5, whether they are similar or not. It's a regression problem. We take the sentences, we represent the sentences as vectors, and we run a simple regression model on top of this. And here what we get is that our results are not entirely competitive. This is basically our result. And the reason is that in such tasks, if you have a repeating word, same order, most of the time it's about the same. But if we take our method and combine it with other methods that take things like word order into account and other type of hand features, we're able to come up with results which are state-of-the-art on this task. The third NLP task that we have is the one of topic classification. We have a sentence in English, and we would like to describe, basically classify it to one of a few classes. So in this case, LeBron James had 26 points. This is a sports sentence. This is a classification task. Here we compare ourselves to a system that was recently published that uses large convolutional neural networks, and we get what seems to be approximately a similar performance, which is much better than the baseline in that paper, which proposed to use word-to-vec in another way. And although we get performance that looks a little bit similar, our advantage is that the system is very efficient and it's very generic. We don't need to train the representation for the new benchmark, where if you use a convolutional neural network for this task, you would need very heavy training of the convolutional neural network for each task separately, and it takes about, well, it's a very heavy neural network to train. So any questions up to this point?
Please use microphone.
So you mentioned the speed before. How do you estimate it? It's an EM algorithm?
It's,
Yeah.
yes.
So the parameter P in the non-Gaussian.
the parameter of the generalized Gaussian distribution is estimated in an EM manner as well, yes. Other questions? Okay. So let me describe what is next, what we are going to do next in this field. So we're about to publish a few new results. The first one is, as I said before, in the example of the semantic sentence similarity, it became clear that using mixture models to represent sentences loses a lot of the information because you don't take into account, for example, word order. So we are actually now replacing the mixture models with recurrent neural networks and come up with much more powerful models which improve, for example, what we get in image annotation and image search by a considerable margin. The second thing that we are working on is to replace the very classical, very powerful CCA algorithm with an encoder-decoder type of algorithm that would map between the image and the sentences. It seems the new algorithm that we have, we compared it with the CCA, regularized CCA, kernel CCA, randomized CCA, and deep CCA, all other algorithms from the literature, and it seems to outperform all of these algorithms. And maybe even more surprising is a very recent result that if we use the shared space, the space that we have from the images and the text, and we encode videos in this space. So although the videos have nothing to do with the task of image annotation, but we use what we learned from image annotation, and through transfer learning, we use it to encode videos, then we are able to improve on the answer of action recognition. What do you see in the video? Is it a person dancing, a person jumping, and so on, by a very large margin. Other results unrelated to this that we are going to have pretty soon is new results in deep optical flow. So optical flow is a very classical computer vision problem, a bit of low level compared to image annotation. We now use deep learning to get very powerful descriptors for local image information, and we combine it to obtain state-of-the-art results in all modern benchmarks in optical flow. The other thing that is coming out is faces again. So we have actually a new loss function that is based on intuitions. In deep learning, we know that the manifold which you are able to recognize is very thin. What happens if you would like to have a more robust solution? So we have a new loss function, and applying it to face recognition, we get improved results. We also have a theoretical framework for transfer learning, a pack theory-like framework for transfer learning, which we use examples from face recognition to demonstrate its effectiveness. And we have another work in which we compress deep neural networks used for face recognition such that we are able to run the face recognition engine on a mobile phone much more effectively. So let me finish here, and I would be very happy to answer any question that you have on any topic that is related to image analysis, text analysis, or any other topic which we work on.
You see, we have the direct translation now, and please use microphones to ask a question.
Okay, I have a question. Lior, you mentioned about compression of neural networks.
Yes.
How much have you managed to compress it? And how much times?
So if we start with a network which is fully convolutional, so there isn't really much to compress over that, which are the networks we currently use for face recognition, we're able to speed it up by a factor of 3 or 4. The memory footprint is not that large in any case, since it's purely convolutional. The speed up is is pretty impressive. There are many other methods in the literature to speed up convolutional neural networks, all sorts of pruning methods, methods for PCA compression, methods based on regression, such as FitNet. We compare with all of these, and we are able to get favorable results.
And what about fully convolutional layers? Have you tried to compress them?
So, fully connected layers?
Yeah, fully connected, sorry.
We don't have such layers in our network, and the methods that we developed are meant to work on convolutional layers.
Okay, thanks.
More questions? Okay. Thank you very much.
Okay, thank you very much.